Right now, as you're, just sitting there listening to the sound of my voice, the actual physical structure of your brain is actively changing.
Oh, yeah, completely. It's remodeling itself in real time.
Right. Chemical signals are just jumping across these microscopic gaps, and new neural pathways are, well, they're being tested out. Millions of cells are firing in these highly specific rhythmic patterns just to turn these audio waves into something meaningful.
And it's wild because the human brain is, widely considered the most complex structure in the known universe. And it's just entirely dynamic.
Yeah, dynamic is the perfect word. I mean, something as simple as like drinking a cappuccino or maybe learning just one new fact, it triggers these massive neuronal events.
Right. And some of those happen in like a thousandth of a second. But then the structural changes they provoke, those can literally take decades to fully unfold.
It's just mind-blowing. Speaking of which, there is this incredible quote from the source material we are exploring today for this deep dive. We're looking at the textbook Fundamentals of Cognitive Neuroscience, a beginner's guide, the second edition.
A fantastic text, by the way. Very comprehensive.
Yeah, it really is. And there's this quote by the British scientist Francis Crick where he describes the sheer scale of all this brain activity. He says, consciousness is somehow a byproduct of the simultaneous high-frequency firing of neurons in different parts of the brain. And he goes on to say, it's the meshing of these frequencies that generates consciousness, just as tones from individual instruments produce the rich, complex, and seamless sounds of a symphony orchestra.
I love that quote. That symphony metaphor really, it really anchors what cognitive neuroscience is actually trying to achieve.
Right, because we aren't just looking at the biology, we're studying the combined output of the mind and the brain together.
Exactly. And throughout this deep dive, our mission is to give you, the listener, a really comprehensive educational summary of this text. We're going to explore the biological framework of that orchestra and the physical mechanics of how you perceive things and learn.
And then ultimately, we're going to wade into the deep waters of the actual machinery behind human consciousness itself.
It's a lot of ground to cover.
It is. So let's just jump right in with the physical framework because, if we want to understand a symphony, we first have to, identify the instruments.
Right, and learn how to actually listen to them.
Exactly. So the text breaks the investigation of the brain down into 5 distinct disciplines. First up, we have neuroanatomy, which is the macro-level study of the brain's physical structure. The cortex, the subcortex, the cerebellum.
Yeah, the basic physical blueprint. And then right next to that, you have neurophysiology. This one zooms all the way into the cellular level to look at the chemical and electrical workings of individual neurons.
Right, but just knowing what the structures are and what the cells look like, that doesn't actually tell you how a thought is formed.
No, not all.
It's like, okay, let's unpack this with an analogy. If you just have the anatomy and the cells, you basically just have a map of a sprawling city and a list of its residents. But you have absolutely no idea what those people actually do for a living.
Yeah, it is a great way to put it.
Yeah.
Which is exactly why we need the third discipline, which is functional neuroanatomy. This one actually maps specific cognitive and motor processes.
Yeah.
So things like language or reading or just moving your hand to those specific physical structures in the city.
Okay, so mapping the jobs to the neighborhoods.
Right. But then you have to understand how those distinct neighborhoods communicate with each other, which brings us to the fourth discipline, neuroconnectivity.
Ah, the highway system.
Exactly. It's the study of the brain's physical white matter pathways. These are massive bundles of nerve fibers that act as the biological highways.
And what's the fifth one?
The fifth is neurodynamics. This is the study of the actual rhythms and oscillations of the brain waves, basically. Yeah. Because, the brain isn't static. Its electrical activity shifts continuously depending on whether you are, say, intensely focused or relaxed or in deep sleep.
So neurodynamics is like watching the flow of traffic during rush hour versus 3 in the morning.
Precisely.
Honestly, trying to understand all 5 of those simultaneously just seems like a massive logistical nightmare. The text actually points out that to be a perfect observer of the brain, you would need to act like a flawless, omniscient spy satellite.
Yeah, a satellite tracking tens of billions of individual neurons firing many times per second,
while simultaneously monitoring the shifting traffic of tens of thousands of signals traveling back and forth. It's just staggering.
And historically, doing that was literally impossible.
No.
I mean, for centuries, neuroscience had to rely heavily on post-mortem examinations. We basically had to wait until a patient with a very specific cognitive deficit passed away and then
and then examine their brain after the fact to see where the physical damage was.
Right. We were always just looking at the aftermath.
But today, the modern tools we use instead are just remarkable. For mapping the static structure, we use MRI and CT scans. But for functional activity, actually watching the city while it's awake and doing things, we use fMRI and PT scans.
Yeah, fMRI is a game changer.
It really is. And I think it's worth explaining how fMRI actually works, because people often think it's just taking a literal picture of your thoughts. But it's not, right? It relies on tracking blood oxygen levels, the Bol-D signal.
That's exactly right. fMRI does not measure neural electricity directly. It operates on this really simple biological principle. When a specific area of your brain is working hard, it requires more energy. And more energy means it needs more oxygen.
So your body just redirects a bunch of oxygen-rich blood to that specific neighborhood.
Yep. And the fMRI machine detects the magnetic differences between the oxygenated and deoxygenated blood. So by tracking where that blood flows in real time, we can infer exactly which parts of the brain are highly active during any specific task.
That is so clever. Meanwhile, we have tools like EEG and MEG that are directly measuring the electrical and magnetic fields produced by those firing neurons, which gives us that neurodynamic picture.
Right, the real-time electrical traffic.
And what's cool is all this data isn't just kept in giant spreadsheets anymore. The textbook highlights this cutting-edge visualization tool called the connectogram. It basically takes all this connectivity data and maps it visually.
Yeah, the connectogram. It maps the brain in this circular format. And I will warn you, it is incredibly dense with data.
You're not kidding? It honestly looks a bit chaotic at first glance. If you're just mapping billions of connections on a circle, it kind of looks like a tangled ball of yarn. Like, how does a neuroscientist actually read that without getting a headache?
Well, it looks chaotic until you understand the sorting rules. It's actually highly structured. The outer rings represent the physical properties of the cortical regions.
Okay, so walking from the outside in, what are we looking at?
So reading from the outer edge inward, you have a ring specifically representing gray matter volume. Then the next ring inward is surface area, then cortical thickness, and then curvature. It's perfectly ordered.
Wow, okay. And then what's in the middle?
The vast inner circle is filled with this complex web of colored lines that represent the degree of connectivity, the actual fiber tracks we talked about, running between those specific regions. So it compresses just an overwhelming amount of structural and functional data into one unified snapshot.
So it's basically the ultimate city map. But okay, if we take this incredible, highly mapped physical structure, how does it actually process the absolute chaos of the outside world? Like, how do we get from a physical stimulus to a complex action?
Right, that transition is key. For this, we use what's called the functional framework of the mind. It's a conceptual model to organize how sensory information is actually processed.
Okay, let's trace a physical event. Let's say a cell phone rings in a crowded room.
Perfect example. First, those sound waves physically hit your ear, and the neurological signal enters your sensory buffers. This is raw, immediate, bottom-up processing.
So you haven't assigned any meaning to it yet. It's just noise.
Exactly. But if that signal is captured by your attention, it gets pushed forward into your central executive and working storage.
And working storage is fascinating because it has very specific tools for different types of data. It's not just an empty room where memories bounce around. The text highlights a visuospatial sketchpad for visual data and a verbal rehearsal loop for auditory data.
Right, so if someone tells you a phone number and you don't have a pen, and you have to walk across the room to write it down.
You're just repeating it in your head over and over.
Yes, you are actively firing that verbal rehearsal loop in your working storage to keep those numbers active.
That makes so much sense.
And while you are holding that sensory information, your central executive is simultaneously reaching into your stored long-term memory. It's digging into your vast repository of semantic knowledge and past experiences to cross-reference the sound.
Right, so it says, hey, wait, I know that ringtone.
Exactly. Once it matches the sensory input to a stored memory, recognizing that specific ringtone belongs to your phone, it moves to action planning, and finally, response output. You plan the motor movement, you reach into your pocket, and you answer the call.
I want to zoom in on that very first step for a second, the auditory sensory processing. The text quotes Hans Christian Andersen, who said, "Where words fail, music speaks," which, is a beautiful sentiment. But mechanically, how does the brain actually know where a sound is coming from?
That's a great question.
If I'm listening to that symphony orchestra Crick mentioned, how does my brain localize the violin section versus the brass section?
Your brain essentially acts like a highly sophisticated triangulation system, relying on two basic physical cues. The first is intensity. Because your physical head actually blocks sound waves, a sound coming from your left will be slightly louder in your left ear than your right.
Okay, that makes sense. Just a volume difference.
Right. And the second cue is a microsecond difference in timing. That same sound wave will physically arrive at your left ear a tiny fraction of a millisecond before it reaches your right ear.
Wow. It's essentially exactly how GPS satellites pinpoint a cell phone's location on Earth, just by calculating the minute delays in signal arrival times from different satellites.
That is a perfect analogy. The brain calculates that interval time difference down to the microsecond. And once the source is pinpointed, the auditory processing physically splits into two distinct neural streams.
Oh, the what and the where streams.
Exactly. There's the what stream that moves down the temporal lobe to identify what the sound actually is, a violin versus a cell phone, and a where stream that moves up toward the parietal lobe to track its exact location in physical space.
Okay, I follow that. But here's where it gets really interesting for me. This whole framework, sensory buffers, central executive, cross-referencing memory, it sounds incredibly mechanical.
It does sound like a flow chart for a computer program.
Yeah. But human thought isn't always this step-by-step explicit process, you know? What about the sudden flash of inspiration, the aha moment? A computer doesn't suddenly have an epiphany while taking a shower.
No, it doesn't. And this brings up the crucial distinction between explicit and implicit processing. Explicit problem solving is exactly what that framework describes. Conscious, step-by-step analytical thought.
You are driving the bus.
Right. You are aware of every step. But implicit problem solving happens entirely below the surface of your conscious awareness.
So how do we know it's actually happening biologically and not just some, like, mystical psychological phenomena?
Because we can actually see its biological footprint now. The text highlights research by Jung Beeman and colleagues who use neuroimaging to study the brain during actual moments of insight.
And what did they find?
They discovered that specific regions in the right hemisphere of the brain showed this massive burst of high-frequency activity immediately prior to the conscious aha experience.
Wait, really? Meaning the unconscious neural networks were actively working on the problem the entire time?
Precisely. Your brain is a pattern recognition machine. Even when your central executive isn't consciously focused on a problem, your implicit networks are rapidly testing associations and patterns in the dark.
That is incredible.
When they finally lock on to the correct representation, they surge with activity and push that fully formed answer up into your conscious awareness. The aha isn't magic. It's just the sudden delivery of a product your unconscious mind has been manufacturing this whole time.
Okay, but a flash of insight is completely useless to our long-term survival if the brain can't physically store it for the next time we face that same problem.
Exactly.
Which brings us to learning and memory. Because how does a fleeting electrical spark actually become a permanent structural change?
Well, memory is defined fundamentally in the text as a lasting brain representation. And to understand it, we really have to look at our evolutionary context. The human brain did not evolve to sit in a library and memorize the cranial nerves for an anatomy midterm.
Right. It evolved for physical survival in a highly interactive, dangerous environment.
Yes. So what does this all mean for the medical student or young professional listening right now who just wants to pass their exam?
Yeah, how do they hack a biological system that wasn't built for academics?
By aligning your study habits with how the brain naturally builds those lasting representations. The text uses a highly practical example involving studying a map of Europe.
Okay.
The intuitive approach for most students is simply to restudy. You stare at the labeled map, you close your eyes, try to hold it in your working memory, and then look again to see if you were right.
The classic brute force repetition method.
Exactly. But neurologically, passive observation is incredibly inefficient. A far more effective method is retrieval. Instead of staring at the labeled map, you take a completely blank outline of Europe and you force yourself to recall and write in the names of the countries from scratch.
But why does the actual struggle to retrieve the information make the memory physically stronger?
Because memory isn't a file sitting in a folder on a hard drive. It's a physical pathway of synapses. When you force the brain to execute the process of retrieval, you are actively firing electricity down that specific network.
Oh, I see.
This active firing triggers a process called long-term potentiation. The synapses literally build more receptors and become more sensitive, making it easier for that specific pathway to fire in the future. We call these excitatory memory traces.
And doesn't it also suppress the wrong answers at the same time?
Yes, it does. When you struggle to remember if a country is, say, Austria or Hungary, and you finally retrieve the correct answer, your brain creates inhibitory memory traces for the wrong answer.
Wow, so it actively weakens the synaptic connections to the incorrect information so it won't interfere next time.
Exactly. You are chemically pruning the weeds while fertilizing the main path. Evolutionarily, we learn by interacting with our environment and retrieving information to survive it, not by passively observing it.
And we categorize this information differently too, right? We have episodic memory, which is the rich sensory memory of specific events like remembering the smell of the room during our first day of college.
Yes, those are tied to specific experiences.
But what we're talking about with the map of Europe is semantic memory.
Right. Semantic memory is your repository of pure facts and conceptual knowledge. Knowing that Paris is the capital of France or knowing the function of the amygdala.
And to manage this staggering library of semantic knowledge without just totally overwhelming the system, our brains build schemas.
Yes, schemas are vital.
I always think of schemas as pre-existing neurological scaffolds. They help us organize related concepts so we don't have to process every new piece of information from scratch. Like, if I learn a new fact about dogs, I don't have to relearn what an animal is. I just hang that new fact on my existing dog scaffold.
Precisely. Schemas save immense amounts of metabolic energy by allowing us to rapidly assimilate new data into established frameworks.
Okay, so we have this incredible physical structure, we have the functional framework to process sensory data, and we have the physical mechanisms of memory to store it all.
We do.
But where does all this processing actually happen? What is the global state of the mind while it's doing this heavy lifting?
This brings us to the deepest waters of the text. Consciousness itself. Bernard Baars, who is one of the editors of this textbook, provided a brilliant metaphor. He said, consciousness is the water in which we swim.
That is a great visual.
It is. It's so pervasive and fundamental to our experience that, like a fish in the ocean, we cannot easily step outside of it to observe what it actually is.
I think one of the biggest hurdles is untangling consciousness from attention. They often get used interchangeably, but they are mechanically very different things.
The text uses a theater analogy to separate them clearly, which I find very helpful. Imagine your mind is a theater. Consciousness is the stage itself. It is the wide open space where thoughts, feelings, and sensory inputs can be seen and experienced.
And attention.
Attention, on the other hand, is the spotlight sweeping across that stage.
This is where we can actually prove it to you, the listener, right now. As you listen to this, you have been entirely focused on the sound of my voice. But until I say these next words, you are likely completely unaware of the physical sensation of your clothes resting against your shoulders.
Or the exact position of your tongue in your mouth.
Right. That is a perfect demonstration. The physical sensation of your clothes was always there, waiting in the dark on the stage of your consciousness.
But you just used your voluntary attention, the spotlight, to bring that specific sensory data out of the shadows and into the bright light of your central executive so you could analyze it.
But the stage isn't always lit, right? Our global states of awareness radically change our neurodynamics, especially when we sleep. Let's talk about what happens to those brainwaves when the gears shift.
Yeah, we mentioned earlier that neurodynamics are often measured in hertz. In this context, a hertz simply refers to a cycle per second, specifically how many times per second millions of neurons are firing in synchronized electrical rhythm.
Okay, so when you are fully awake and alert...
When you are awake, your brain exhibits beta waves, which are fast, firing at greater than 13 hertz. When you relax and close your eyes, it slows into alpha waves between 8 and 13 hertz. But as you transition into sleep, the machinery profoundly changes.
Right. During REM sleep, rapid eye movement sleep, your brain drops into theta waves at 4 to 7 hertz.
Exactly. And then we get into the non-REM stages. Stage 2 is characterized by something called sleep spindles.
I've always found sleep spindles fascinating. They are these sudden, intense bursts of electrical activity firing at 12 to 15 hertz, just bouncing between the thalamus and the cortex.
And finally, you descend into non-REM stage 3, known as slow-wave sleep. This is where the brain emits deep, sweeping delta waves at less than 4.5 hertz. And it's important to note, this isn't just the brain shutting off to save power. This is an active, critical biological process.
Oh, absolutely. The text emphasizes that it is during these specific biological rhythms, particularly the slow-wave sleep and the sleep spindles, that memory consolidation actually occurs.
Right. Throughout the day, your hippocampus acts like a temporary hard drive, holding on to new semantic and episodic memories. But during those deep, slow delta waves, the brain physically transfers that data from the short-term hippocampus to the long-term storage of the cortex.
Solidifying those synaptic traces. So if you do not sleep, you physically cannot lock in the memories you studied that day.
You literally can't. The mechanism requires that specific state.
It's sobering to realize how heavily reliant we are on these specific global states, which means we have to address what happens when the system is damaged. The text discusses disorders of consciousness, or DOC.
Yes, DOC is a critical area of study.
Often, we think of consciousness as a light switch. You are either completely awake or you are knocked out. But clinically, that's entirely inaccurate.
It is a profound misconception. Disorders of consciousness are a continuum, and they are built on two distinct, separable facets: wakefulness and awareness.
Okay, break those down for us.
Wakefulness is dictated heavily by the brainstem. It is the basic physiological state of being awake, having your eyes open, exhibiting basic reflexes, and maintaining a sleep-wake cycle.
And awareness.
Awareness, which relies on the higher cortex, is the actual content of consciousness, the internal experience of thoughts, emotions, and sensory perception.
Because they rely on different structures, they can be decoupled.
Precisely. For example, a patient in a vegetated state might exhibit wakefulness, their brainstem functions, their eyes open in the morning and close at night. But due to severe cortical damage, they entirely lack awareness.
So they are awake, but the stage of the theater is completely empty.
Exactly. Understanding this mechanical separation is vital for clinical diagnosis. On the far end of the spectrum, you have deep coma, where both wakefulness and awareness are entirely absent.
That is heavy, but so important to understand. To wrap up our understanding of this immense system, the text emphasizes one final, overarching truth. This machine does not develop in isolation.
Right. We are fundamentally a social species.
We don't grow up in a vacuum.
No. Brain development is driven by the constant bidirectional influence of nature and nurture. Your genetics drop the blueprint, but your environment and your social interactions physically wire the connections.
And because we rely on group cohesion for physical survival, human beings develop a specialized social brain incredibly early in childhood.
Yes. We have dedicated high-speed neural pathways just for face perception. We have specialized circuits for detecting the exact direction of someone else's eye gaze, and networks dedicated to predicting the intent behind their movements.
Which is wild. Even before an infant can speak, their brain is rapidly wiring itself to read emotional cues and navigate the social dynamics of the humans around them.
Because identifying a friend versus a foe was the single most critical survival skill our ancestors had.
It all routes back to survival. Well, let's take a breath and review the functional blueprint we've built today.
It's been quite a journey.
It has. We started with the 5 disciplines of observation, moving from microcells to macro pathways, mapped out beautifully by the connectogram. Then we walked through the functional framework, where sensory buffers hand data to the central executive, utilizing GPS-like calculations to localize sound.
We explored how implicit networks operate in the dark to hand us sudden aha moments.
We established the physical synaptic reality of excitatory and inhibitory memory traces, proving that active retrieval physically changes the brain. And finally, we waded into the theater of consciousness, the absolute necessity of delta waves for memory consolidation, and the early wiring of the social brain.
It is a massive amount of highly technical information. And because we established that simply listening to us summarize it will not trigger the long-term potentiation needed to remember it, I actually have a short exercise for the students and professionals listening.
Ooh, time to utilize active retrieval.
Exactly. When this audio finishes, I want you to take out a blank piece of paper. Without looking up the answers, I want you to try to sketch out the functional framework we discussed.
Draw the mechanical path.
Right. Start at sensory input.
Yeah.
Where does it go next? How does it reach the central executive? What are the 2 specialized tools, working storage uses for visual and auditory data? And finally, how does it connect to long-term memory to produce action planning?
The momentary struggle you feel while trying to remember those specific terms is the exact mechanism strengthening your neural pathways.
Hack your biology.
Love it. Well, before we sign off, I want to leave you with one final thought inspired by the text to mull over on your own. We established that memory evolved for physical survival, right? And we now know, thanks to neuroimaging, that a sudden flash of insight, the aha moment, has a very specific, localized biological footprint.
It is a physical, measurable event in the brain.
Right. So, if we know the exact electrical and chemical signature of inspiration, could future neural technology ever allow us to manually trigger it?
Oh, wow.
Like, could we one day bypass the arduous process of explicit study and use targeted neurodynamics to simply induce the biological state of pure understanding?
That completely flips the concept of learning on its head. If the brain is a machine, there is always the potential to artificially activate its most complex functions.
It's an incredible, slightly terrifying scientific possibility. Well, thank you for joining us on this deep dive into the fundamentals of cognitive neuroscience. Keep your attention spotlight bright, prioritize your slow wave sleep, and never stop listening to the symphony of your own mind.